So a problem with the last approach is that I had to use PowerPoint, and that meant I had to prepare the slides in advance. Um, that has two issues with it, or two potential issues. One, there's not that much flexibility. Once it's set up, you've got to stick with what was prepared. And two, we have to prepare it in advance. And if you don't get time to do that during the school day, you're going to be doing that in your evenings or weekends. And maybe I don't want that. So whiteboards are often a really good option. So maybe there's another way that I can use a whiteboard, or in my case, a tablet, to present the examples a bit more quickly, a bit more efficiently by changing the examples. So I'm going to give that a go next, keeping most of the things the same. I'm going to use slightly different language to last time, but broadly the same. And then we might look at a few other ways we can vary this as well. I'm going to show you what we mean by the words quadratic equation. So to begin, this is not a quadratic equation. How do I know? Because the highest power on the variable is not 2. But now I'm going to change just one thing. Watch what I change. This is a quadratic equation. How do I know? Because the highest power on the variable is 2. I'm going to change one thing again. This is still a quadratic equation because the highest power on the variable is still 2. I'm going to change one more thing. This is still a quadratic equation because, again, the highest power on the variable is 2. But now, I'm going to change just one thing. Watch what I change. This is not a quadratic equation because the highest power on the variable is not 2. Okay, by changing the example set, my positive examples were not maximally different anymore. They were all actually minimally different. Now, on the plus side, that meant that I could use an awful lot more continuous conversion, and it was much faster to do that. So I've reaped some real benefits there. Also, I suspect that it might be possible even to do this without, I could possibly even not use the language, and this might be more successful than the original set. Let's just take a quick look at what that would look like. I'm going to teach you what we mean by the words quadratic equation. To begin, this is not a quadratic equation. I'm going to change just one thing. Watch what I change. This is a quadratic equation. This is a quadratic equation. And this is a quadratic equation. But this is not a quadratic equation. Okay, so there's pros and cons to these two. I think I would probably go with introducing the language in this instance. There's still quite a lot going on. The downside of introducing it is it slows down the number of examples I can present in a given amount of time, and it does introduce a certain amount of interference from example to example. I can't just go, hopefully with that second set, you see that I can go from one example to the next quite quickly. I'm a bit limited by the iPad, but I think with a whiteboard it would actually be even easier, even faster, sorry, a bit more slick. But between the two, I would probably, I still think there's just too much going on with equations like this. Too many, 1, 2, 3, 4, 5, 6, 7, 8, 9, 9 symbols at least. I think there's too many things that one could still attend to. So I suspect this would have a much better probability of success in having maximally different positive examples. I would probably still state in Word, I'd use a correlated feature sequence, and I'd say, this is how I know it's quadratic. I would probably use an example set like this. The maximally different example set, if it works, is better. If it works, it's better because it is presenting a much broader range of what can be classified as a quadratic equation. Whereas the example set I just presented, if I quickly try to draw them all out now, so I didn't prepare this in advance. Okay, they're all very, very similar to each other. There's a lot of what's called stipulation here. It creates something called a stipulation problem. Technically, I'm stipulating that to be a quadratic equation, it must have an x, because I haven't presented any examples that aren't an x. I don't have an x as the variable. Next, I'm kind of technically stipulating that there has to be a 4 and a 7. I'm stipulating that it has to be a binomial on the left and a monomial on the right. They're so similar that it's creating the impression that these things matter because I keep repeating them. Despite that, I think I would probably use an example sequence like this. I would use this because it's easier to present using continuous conversion. It allows me to direct attention to little things each time. And then you've got a choice. I would either introduce a short second sequence. We'd do some testing, we'd do some initial testing sequence, then either introduce a very short second sequence that starts to vary other things, or possibly rely on the expansion sequence. So depending on how the class I'm teaching, and there's always a bit of you're placing a little bit of a bet when constructing an expansion sequence. It's always, I'm showing them something they've not done before. What are the odds that they're going to be successful? So I might say, is this a quadratic equation? Yes or no? How do you know? Is this a quadratic equation? Yes or no? How do you know? Um, is this a quadratic equation? Yes or no? How do you know? Is this a quadratic equation? Is this a quadratic equation? Um, this would allow me to start changing things. Is this a quadratic equation? It would allow me to start changing things without having to do more instruction from me. So they're kind of figuring it out for themselves based on what they've seen so far. There's an element of taking a best guess, which is why there's risk involved here. Um, but based on everything you've been presented so far, what's your best guess? Is this a quadratic equation, yes or no? And if they're 100% of them keep getting it, great, this is working. If any of them don't, then we take a different course of action in order to make sure they get it. This last one that I've put up here, I think is quite an interesting one because I think actually my bet would be maybe half the class, depending on which class I'm picturing, would get this wrong. It's what I call a kick yourself mistake. I don't think they'd be getting it wrong. I think they'd be getting it wrong because they wouldn't be attending deeply enough. They would just be used to seeing if there's a power bigger than 2, then it's not quadratic. So I might include this even though I know that lots of them are going to get it wrong. But then it's just a bit of a, oh, really? Check, what do we say? Highest power in the variable. Oh, yeah, no, I see how I got that wrong. So, yeah, I just think that's a good one to include. And then you can expand it. We could expand it further. So we've got, is that a quadratic equation? And so on and so forth. So just to summarize that, between the original example set, which was maximally different positive examples, versus this example set, which was actually minimally different positive examples, I think I would try this first, and then use the expansion sequence to further demonstrate maximally different positives. But that being said, if this worked, if you had a different view and said, I want to do it this way, and it worked, then kids are going to learn faster this way, which is a good thing because they're seeing much more variation much more quickly and following it and and getting it 100%. One final thing on the language, I've stuck with what you suggested to begin with, the highest power in the variable. Strictly speaking, and I think the precision does matter, these are not variables. And they're not variables because everything we've presented so far has been a conditional equation, which means this is true. The statement of equality, equal sign, is true only on condition that that x takes a certain value. And if it takes any other value, if this is 100, then this is not true. Therefore, x cannot be 100. And in this instance, it's actually really limited to just a single value. With the quadratics, it could potentially take two values, but still, it's a very sort of finite set. I'm a little unsure actually whether it's still classed as a strictly an unknown or a variable if it can take on more than one value. But generally speaking, I just tend to stick to unknown if it's one of a very clear finite set. And then if you introduce a second unknown like this one, these can now vary in relation to one another, so they become variables. You can imagine that the parabola, you could take any one of an infinite number of points along the parabola, and that'd be true. So in future videos, if I use the language, I'm going to switch now from variable to unknown.